Good afternoon, ladies and gentlemen. So it's my pleasure to introduce Marco Morandotti from the Polytechnic di Torino, who is already second time here, I guess. And today he will speak about the topic from his wide range of interests, and it will be the game theory.
Thank you very much, Martin, for the presentation and the introduction, and I'm grateful to be here giving my second Nečas seminar. It's always good to be back in Prague. And so today is not going to be a talk about continuum mechanics, but something different, which I've been studying for a few years now. And the topic is say, game theory and some derivations of it. And I started it when I was doing a postdoc at the Technical University of Munich 5 or 6 years ago. So, okay, so the outline of the talk is going to be the following. I would like to introduce you to the replicator equation, and then I would like to show you how to extend the context of the classical replicator equation when we also include spatial dependence. So that's why we called it spatially inhomogeneous replicator equation. And then the main aim of that research was to try and see if we could prove a mean-field limit result in the spirit of mean-field games, but slightly different than that of the theory of mean-field games, on the classical one by Lazarelli-Ons and Mayameka and Ken and Wang. Then we moved on to mean-field optimal control, and then as a few other applications, we could address the case where we add some entropic term that acts as a regularizing effect. And I would also try to look at systems with diffusion because they bring back second-order terms which we disregarded in the first place, but are those that are typical from the Lazarelli-Ons theory. Also, let me just mention that I don't see anyone from home, so if you have any questions, just interrupt and ask, and I'm happy with this. And I would like to acknowledge all my co-authors, but I will do that as the seminar progresses. So the replicator equation comes from a biological motivation. Maybe I can minimize this. Okay. Comes from a biological motivation where we want to look at how strategies perform well when chosen to play a game in a way. And the game is a two-player game, and this is encoded in the fact that this payoff J depends on two variables. So assume that we've got a finite number of strategies available, U1 through UN, and we want to do how one strategy does better compared to the average of the strategies that I can play. So what do I do? I do this. I average out the payoff of my strategy UI against all the opponent's choices UJ, which happen at a frequency sigma j. And then I subtract from this the average over all of my other strategies when I sum over UL over L from 1 to N in this way. So now this delta thing is a number and it has a sign. So if delta is positive, it means that my strategy UI does better than the average of the strategies that I can play. So I would like to keep it and enhance it. Whereas if the delta is negative, then my strategy UI performs in a poorer way compared to the average that I can play. So say that I draw another strategy at random, I would do better in that case. So I would like to progressively suppress my strategy UI that performs poorly. So the idea is encoded in this replicator dynamics or replicator equation, which can be say learned from Bauer and Sigmund book, and it's like this. So the evolution over time of the frequency at which I studied my strategy, at which I play, sorry, my strategy UI, which is sigma I dot, depends linearly through this kernel on the frequency itself. Actually, it's not quite linear because there's a sigma j, there's a sigma L here, which also encodes the sigma I, so that there's the dependency is not quite linear, but the form is like this. So the delta also depends on the sigma I and depends on also all of the sigmas that are involved. And now one can bring things to a slightly more complicated level, and the natural generalization from a finite set U is to consider a compact metric space. So we call it capital U. And strategies now are defined in the sense of mixed strategies as they were introduced by Nash to prove the existence of Nash equilibria. So now a mixed strategy in this case would be a probability measure on the space capital U, right? And a mixed strategy in the finite case is also a probability measure here, but it's a convex combination of the elements U1 through UN. You just need to choose weights which add up to 1. It's like having a financial portfolio, and then you want to choose the way you allocate your wealth. So you choose to, I don't know, allocate half in bonds, a quarter in stocks, and the remaining quarter, either you have it in the bank or you buy apartments or something like that. So you need to exhaust all of your wealth. So that's why the probability measure is the best tool to represent this. And then we want to study how this probability measure evolves. And this can be seen as the mean field limit when the number of strategies diverges. So if I have finitely many of them, I take the empirical measure associated with it, which is a combination of deltas centered at the points uj. And then I would like to study the limit as n goes to infinity. So to do this, I consider my initial strategy, say in the continuum sigma bar. I want to approximate it by empirical measures, and this I can do in the sense of measures. And then I say that the evolution of sigma t is given by the limit of the evolutions of the sigma t n's as n runs to infinity, and I verify this in the weak sense. So basically, I tested in the sense of measures with sufficiently irregular functions phi, and I want to recover the evolution through that equation there. All right, and this was proposed by these authors in the references there, and it's a good notion to try and see how this probability measure evolves. So what we did with Luigi Ambrosio, Massimo Fornasier, and Giuseppe Savare was to consider a system now where instead of just having strategies or probability measures of strategies, we also track the spatial evolution of the agents. So the status of the system is a pair, x and sigma, where x is a position in the space and sigma is a mixed strategy, say on over the probabilities of U. And I call this one capital Y, and the element of it, I call it small y. All right. And then I want to consider a distribution of players with their own strategies, which is a probability measure on the capital Y space. So it's P of RD cross P of U. Okay. And the idea of the game is to see how this capital sigma object evolves over time. And now we need to also consider a space-dependent payoff, capital J, which is no more a function of 2 variables, but of 4. So 2 are special positions, and then there are the strategies. And the kernel now can be represented in this way, which is the continuum generalization of the previous one with the sums, also including the fact that I'm integrating over space. So basically, this tells me if I am player X and if I'm sitting at position X playing my strategy U, J of X U U prime, X prime U prime tells me how much I gain from playing a 2-player game with somebody positioned at the location X prime playing strategy playing strategy U prime. Okay, so then as before, I need to average over all the frequencies at which U prime is played. And then since there's the distribution on top of this, I also have to average over these guys. Right, so averaging in this sense means taking the integral with respect to the sigma because it's a probability measure. And then I take away the average if I make all my possible strategies W run through my possible choices. So I also integrate once more with respect to this sigma of W, and this is the same thing as doing this second integral, the second summation here. All right. And the evolution is the same formally as the one that I had before. It's sigma dot equals the kernel delta applied to sigma. But now we also need to track the spatial displacement of the agents. So we want to say that if we have a velocity field A that depends on sigma possibly and on the state of the system Y, then I can prescribe the law of evolution here, the velocity of the spatial variable in this way, and therefore the full evolution is given by this equation here, all right, which is in a way a vector equation of 2 components, but it's really one single ODE for the state variable Y. right? So y evolves according to a field, a velocity field, which I call b sigma. And this is a very simple form of an ODE. It's basically y prime equals b of y. And we all learn how to study this in the first classes of calculus or analysis. But now the functional setting is much different, because if in the special component I have RD, then in the measure component, I have a measure indeed. So we need to be able to find a machinery that allows us to study evolution of probability measures. And in this paper, as I mentioned before, with Ambrosio, Fornaziere, and Savary, we set the basis for finding a proper setting in which to study this ODE evolution. And since the new thing was to tackle the measure part, we decided to keep the spatial velocity quite simple, and we chose a very easy form of the field. In particular, what you have to notice here is that the field A does not depend on the full distribution of agents with their own strategies. But then together with Francesco Solombrino, we generalized the framework for allowing a general dependence on the sigma as well. And also in that paper, we provided some relevant examples that sort of put together a bunch of things that were out in the literature before, namely the compact metric space or the finite number of strategies, or also when the finite number of strategies just reduces to 2, you can say that you have some sort of a leader and follower dynamics, which is a model that's very popular in applied sciences, also for studying social behaviors. So what is this generalized framework? What we wanted to give were general hypotheses, like minimal ones, in order to have the theory to provide existence and uniqueness of solution, and then eventually recover the mean field limit that we proved in the first paper with Ambrosio, Fornaziere, and Savary. The dates are a little bit misleading, but temporarily this one happens before the other one, but it took ages to be published, so that's why the dates are inverted. So the first thing that I want to show you, though, before getting to the generalized hypothesis, is a heuristic way to recover the evolution. All right. So we notice that this nonlinear continuity equation, which is the continuity equation that drives the measure sigma, can be actually obtained with this process. So we need to think what a player would do if they were in our setting, and see how we can build say approximate the solutions in small time steps. So in a small time step H, you would like to do some sort of explicit scheme where you say I update my velocity and I do one step, and then I update some other things, and then I get in the new state, and then I do this. So now, since the state is composed of two objects, the x and the sigma here, I assume to be sitting at x bar sigma bar when I observe the state. And then the first thing that I do is that I want to upgrade the strategy. So the strategy is upgraded by one step of the replicator equation. So I take my sigma bar, and it's 1 plus h delta. That would be the differential of the velocity, and I land in the strategy sigma bar prime, which is the updated one. So one important thing to notice is that since sigma bar is a probability measure, I also want sigma bar prime to be a probability measure, and that's the tricky part. But the replicator kernel wonderfully does the job, because it's if we average out once more, we get 0 basically, because if we integrate again, so if here I integrate again over the space u in the sigma of u, then I get the same term, because the sigma of u is a probability measure. So this one comes out as a constant, and I get 0. So this object here is with 0 average. And it's natural to expect and actually to demand this, because the space of probability measure is not a flat space, it's a curved one. So in order to be moving, then you need to move along the tangent, and the tangent to the probability measures is the space of measures which have 0 average. Okay, so we do this and we land into a new distribution, a new mixed strategy, if you want. And then according to this new sigma bar prime, I update my position, I update where I go. So I do one step of spatial update, which is this one, x bar plus h times the infinitesimal velocity, say, where the strategy u here that determines it is drawn according to the new measure. So ideally, one example could be, I am in a room and I want to find the exit of the room. And maybe I don't know which way is the straight way to go, but then I have to explore the space a little bit. So first I look around myself and I see the environment. And then with the new knowledge that I have when I saw the environment, I can decide in which way to go. So if you have a column or an obstacle in front of you, then most likely, and you want to go through it, then most likely you will have, say, go left and go right as possibilities, and then you choose the direction to go at that step according to those. But if you updated your knowledge of the physical space around yourself by updating the strategy space, actually the mixed strategy, then you know that going straight, like hitting the obstacle, wouldn't be an option. So that strategy would not be available, and then you have to choose the direction given on the other one. When you pass the obstacle, maybe go straight is an available strategy, and you will choose it with a higher probability. And the equations are responsible for fitting all of this. So now there are a little bit of a technical assumptions, but then the velocity E and the delta kernel should be bounded. And if that happens, then this MH, which is the push forward of the evolution at time t here of the initial distribution, happens to be concentrated on paths that share an equilipsis property. So then one can bound them, and we can write down the evolution of the measures in this way by testing against C1 functions in a suitable pressure space, because now everything is in a Banach space. All right. So if one carries out these computations here by keeping this line into account, this line here, then you get that you can pull out factor h, and then you're left with the derivative of the test function multiplied by the velocity field b. So if you bring h to the denominator in the left-hand side, and integrate by parts in the right-hand side, then the derivative falls on the b and the sigma, and the equation that comes out is the continuity equation, which is written down. All right. So this is I think an interesting way to show how this equation is the natural one to appear, because we can do it incrementally, and also this suggests a process for numerical discretization of the problem. All right. So we have this continuity equation endowed with the initial datum sigma naught, which is our initial distribution sigma bar. Okay. Now the hypotheses that we managed to single out are the following ones. So the velocity, now I'm changing the notation a little bit, because this one with the sigma standing for strategy is much more suited for say game theoretic approaches or biomathematical ones, but now I want just to consider general systems in this way. So where I have a probability measure that evolves, which could be a label, I usually call it lambda now, and the position, and then I call psi what used to be the capital sigma. So now I want that the velocity field in the right-hand side of the spatial coordinate is v psi, that depends on the state. And then I take t psi, which is the one that drives the evolution of the probability measures. Now, f of u is a space which is called the RNCL space, and it's a suitable closure of the space of probability measures, because the space of probability measure itself is a little bit too small to carry out this evolution, and we need to take the closure of the finite linear combinations of probability measures. So the hypotheses that are the good ones for making for setting a theorem of existence and uniqueness of solution are the following ones. So we want the fields to be Lipschitz with respect to all of their variables, right? And then we also want the fields to grow at most linearly. And so both of them in absolute value will be bounded by the blue quantity. Also, there is this thing that's the tangency condition, that the t field, the t operator, the transition operator between measures tested against constants should give us 0, and this is telling us that it's got 0 average. It's what we obtain when we want to move along the tangent plane to the space of probability measures. And then there's a technical condition, which is this convexity thing, because the capital Y space, which is Rd cross the probability measures on U, is a closed convex subset of Rd cross f of U. If we take, say, players sitting within a ball of radius capital R at the beginning, then they stay in a compact set, and then the space of probability measure has nice properties. So what we want to have is that we never leave this closed and convex set, right? So this must be phrased in the following way. It can happen locally. So for every capital R, there exists a delta such that for all the measures and the states that happen to be in that ball of radius R in the space Y and probability measures with finite first moment, then when we do this operation, we're still positive, which is equivalent to say that there exists a theta such that Y plus a theta, the velocity field, never leaves the space Y where we stay, the space capital Y. Okay, so this one allows us to apply a theorem by Brezis that studies the evolution of ODEs in Banach spaces. And these are all the conditions that are needed to apply that theorem, which tells us then that a solution exists, it's unique, and we can also get continuous dependence on the initial data. So basically, we managed to prove in all this in these two papers the well-posedness of the particle system here, the particle system, because I call it the particle system because you can think of Y as a particle in the space. Also the one for the capital psi, so this is the continuity equation at the level of the measures. And you notice that here the velocity field that drives the particle evolution, the Lagrangian description, is the same one that drives through the divergence term, the continuity equation, which is a more Eulerian description of the system. And speaking of Lagrangian and Eulerian solutions, we can actually prove the equivalence of the two notions of solution. So the notion of Lagrangian solution would be, you take the flow map associated with the particle system in the left-hand side, you take the push forward of it, apply it to the initial measure, and that gives you the measure, the sigma at time t. Whereas we call a Eulerian solution a weak solution of the continuity equation. So when we test it against suitable test function. And the two notions of solutions are the same. So if you take the push forward given from the Lagrangian formulation, you plug it into the Eulerian solution, then it works. And proving the uniqueness of Eulerian solution was the hard part for which we needed to resort to very technical tools. And finally, the mean field limit is just, I say just because it seems easy to obtain, but it's just a byproduct of the continuum dependence on the initial data. And in the next slide, I'm going to show you how this is the case. So if we have a finite number of players, say capital N, we track the evolution of each of them by the particle evolution indexed by I. And then we associate with the system the empirical measures. So the psi bar is the initial one, and the psi n bar, and the psi nt is the evolution at time t of this empirical measure. So I have capital N agents that move around in the space according to the machinery that I did, driven by the B field. And then we have the continuity equation, which is the one driven by the field, the B psi, right? So which is the one generated by this. So then if you send basically, so continuous dependence on the initial data tells you that if you have two different initial measures of psi1 bar and psi2 bar, then with a very bad estimate, which usually comes from the Rombal lemma, then you obtain that the distance at time t can be controlled by the initial distance at the cost of a very big constant possibly, but still you have this sort of continuous dependence. And so the idea would be that I have a measure in the continuum, I approximate it with empirical measures. So in the right-hand side here, I would have that this distance is becoming, the Wasserstein distance is becoming very small, and therefore also the evolutions become closer and closer. And when does this happen? When n tends to infinity. Okay, so the idea is pretty much this one. All right, so this is what is called the mean field limit. That's the what people in more traditional branches of game theory want to study. They start from a finite number of agents and they want to see how that evolves. One main difference with respect to that theory is, again, that we only have first order equations as opposed to second order equation. And the theory by Lazari-Lyons and Keynes, Mayame, Wang actually has a Laplacian term in here, which mostly arises from diffusion. but we don't get it in this case. And the responsibility for this is that, first of all, we neglect the diffusion effects, and second of all, in the heuristic, here in the formal derivation, there's this factor h that comes out from both parts when we substitute and we approximate that just gives one-time derivative, and there's a divergence, like a derivative here, which gives us the divergence and no extra terms of higher order. Okay. So I just want to mention a little bit where the interesting mathematical things are, but it's very difficult, so I don't think I want to indulge in the proofs or anything particular. So we need to perform some differential calculus in the space Y, which happens to be a convex subset of a Banach space. We don't know if it's open, and that's why that condition that pushes us in is needed, the one with the theta that I showed you before. Then the uniqueness of Eulerian solution can be achieved in two ways. One is working by duality. And this works well for sign measures, can be generalized to sign measures, but also needs a slightly higher regularity of the fields. So it requires C1 regularity, whereas we wanted to get only Lipschitz ones. And the method for this can be drawn from the Green Book by Ambrosio Gili Savare on gradient flows, and there's a chapter where they study the say probabilistic representation of the solutions of the continuity equations where they work by duality. The other one is by using the superposition principle. And the superposition principle only works for probability measures. So all the red things are drawbacks of the theory, if you want. So not sign, but just probability measures. But it has the great advantage that almost no regularity is needed on the vector field B, right? So this can work on under very general regularity assumptions. And the examples that we provided in the work with Solombrino were mostly leader and follower dynamics. So the space of strategies U is a set with two elements, call them follower leader, call them 0, 1 is the same thing. And this we managed to so in this say framework we managed to account for level switching, which means that when leaders become followers or vice versa, and this is some phenomenon which is typically happening in politics, for instance. So at some point there are some politicians that become more and more popular, so they would be rising to be leaders, and then maybe they fall in disgrace and they go back to being followers and nobody listens to them anymore. But the fact that they are leaders at some point allows them to have much more influence and to draw people to their ideas. So in such a context, the sigma now lambda is a label that tells you your degree of leadership in a way, and the spatial coordinate x could just be a point in the interval -1, 1, which can be a model for far left to far right, say aggregations in the political government or something like that. All right. And we also can make a relationship to Markov chains if the transition map T, which in principle depends in a very complicated way, both on the probability measure psi and on the state space Y, is indeed linear in lambda. So if this is linear in lambda, and also if it does not depend on time, then T or its adjoint can be seen as a Q matrix and can be integrated with very well-known formula, and people that study Markov chains probably know this more than I do, but this context allows us for a little bit more generality. Then this case where U is a finite number has a finite number of elements is called the case of multi-level population. So there can be in politics again there can be different parties, or one can study populations with many traits, and this can be accounted for. It's not very complicated, and the theory also allows us to go, say, to include a compact space case, which includes a continuum of labels, and this touches base with the replicator equation as I introduced it when we wanted to get the spatial dependence. Okay, so now I want to discuss a few extensions of the model, of the basic model that I presented so far, and these are all subsequent works with my collaborators. And one thing is that we want to control the system. So the example that I made before about leaving an environment can also be considered in the case of, say, an airport or a very complicated, an environment with a complicated geometry in which the players not necessarily know the geometry of the environment. And so the idea is that maybe if an alarm goes off and there's an emergency, the population of the airport needs to be evacuated as fast as possible in order to prevent damage of some sort. And I think it's a common practice to have some sort of dormant agents mingled within the population that should an emergency happen, that might signal themselves, that might become visible and say, I know the geometry of the airport, follow me to exit. And so as the airport manager, you would like to have as many of these agents as possible to drive as many people in a short time, but also you want to not to spend too much on these. So the idea is that maybe I can activate a control field, UI, for some agents, and then I need to optimize a resource, all right? So then the control field can be included here. So I can change the velocity of the agents by adding this red term UI, and then the age can tell me whether I need to activate it for a certain agent or not. So this activation function in principle depends on the agent itself and on the distribution of the agents in the sense where they are in the space. All right. And the cost function that needs to be minimized accounts for a Lagrangian cost that depends on the positions of the players and on the general distribution of agents, and also accounts, let's say, it's composed also of a cost that is the cost of the control. So how much I need to pay for activating my controls. So there are a few standard hypotheses that are needed here. So ln should be continuous and symmetric in some probabilistic sense, and the phi should be taken positive, convex, superlinear at infinity and zeros. But these are just technical. And the result that we obtain together with Giacomo Albi, Stefano Almi, and Francesco Solombrino is the following: that as the number of agents diverges to infinity, the functionals that I wrote down before gamma converge to this other functional here. Sorry. Yes. Sorry about that. Okay, yes. So gamma converges to this functional here, which has this expression. And in this, the distribution of the player's psi and the cost, say the limit of the costs, are coupled by the following blue equation. So we still have a continuity equation, but now the divergence of B psi is given with a different B, which also accounts for the controls and the activation function that we had on them. Okay, and this extends some results on mean field optimal control. That was a concept introduced by now a very popular paper by Fornasier and Solombrino dating back to 2014, and also addressed later on by Fornasier, Lesini, Urieri, and Savare in a similar context. And as a person coming from a very variational background, I would like to highlight that the minimizing pair psi w for the limit functional here actually can be obtained as a limit of minimizing pairs yn un of the approximating energy, because a gamma convergence result is in place. So if we have we can obtain that minimizers converge to a minimizer of the limiting function. Then the addition of entropy actually happens as a regularizing effect. So I never mentioned something before, but I don't know if it was clear that when I write the replicator equation as sigma dot equals delta sigma, the one at the very beginning, we are assuming that sigma is not negative. That there is a little bit of a fraction for each strategy that is played, right? Because if you got that the sigma, even in the finite number of strategy case, if sigma I is 0 for some I, then it will never activate because its derivative will always be 0. So also for numerical applications, it's interesting to keep this in this way. So we would like the strategies not to go to 0, not to get suppressed strongly, and in a way that the probability measure on those strategies should not account anymore for the one that has been indeed suppressed. And one way to do so is by introducing an entropic regularization. And as I say here, it's proposed to avoid the degeneracy of labels in this way, right? So one can do this following the paper by Bonafini, Fornesian, and Schmitz by considering the reference probability density, eta, right? And the densities L that are diffuse with respect to that, so that they have a density in the L1 or LP sense. And then we take the entropy functional, H of L, where we have the entropy, that's the term written in green, the typical rho log rho entropy, and we average out by taking away this one. And then the entropic regularization now for the labels modifies the second equation. So we take the transition map as I had before, and then I add a smaller perturbation epsilon multiplied by this entropic regularization. And I also put there a factor rho, which is accounted for in the paper by Bonafini, Fornesian, and Schmitzer, for a certain effect that I mentioned in a second. But so the idea now is that we can modify this equation here and study what happens in this case. And this is associated with a velocity field, which depends on these two parameters as well. So together with Stefano Almi, Francesco Solombrino, and Claudio De Ramo, who was a student that did his master thesis on this topic under my supervision at Politecnico. He's very bright, but we lost it to a company. So we lost him to a company. So we proved the well-posedness of the particle system, which is associated with this case, and we proved the convergence to the mean field equation. Now if rho is equal to 1, which has the same form, and the B epsilon is the one that one expects. So the hypotheses are essentially the same. But then for keeping into account this entropic term, the convexity one needs to be adjusted because of this H term acts. And so basically the delta or theta terms that I had before need to be a little bit modified. It's in the same spirit. And if rho is bigger, so rho measures, let me go back one moment. Rho here measures say the speed at which the level update happens. So if rho is very, very large, then you can think that the update of the strategies happens with infinitesimal speed. So as soon as something happens, then the label is updated. So if we take this one, the rho bigger than 1, we also can treat the label dynamics of replicator type, which happens to have this sort of structure, which is a little bit complicated to understand, but the measure nu that appears here is the push forward of the distribution psi, and we have convergence to what's called the fast reaction limiting dynamics, which really does not involve the label dynamics anymore because as they are updated instantaneously, so they don't need an ODE or like a differential equation for governing them, and this can be treated, and that's an effect that was studied by the people that proposed this model, Bonafini, Fornesier, and Schmitz. The last thing that I want to say, and maybe it's kind of a good place to finish now, is adding diffusion. So as I mentioned at the beginning, we don't take diffusion into account, but diffusion effects that we see every day. We walk in the streets with our mobile phone and we know where we want to go. So we have a sort of deterministic velocity, but then looking down on the phone, we just wobble a little bit around because we're distracted. We want to avoid people bump into us or something like that. So the idea is that this can be modeled by adding a diffusive term, which at the level of the PDE transforms it into a Fokker-Planck type equation, where the diffusion intensity is sigma and detects so it multiplies the Laplacian of the measure, and this one is the say continuum counterpart of the probabilistic stochastic differential equation, which is given in these terms. So we have the V, which is a deterministic velocity, and then we have root of 2 sigma, and WT is the Brownian function. So we can notice that this gives both a nonlinear and a non-local character to the equation, which makes it very more interesting to study. And this has been done independently by Ascione, Castorino, and Solombrino, where they studied a multi-agent system with additive noise. So we just add this term here. And they have two populations, capital X and capital Y. Capital X are morally the followers and get sent to their number is sent to infinity. Capital Y are the leaders, and their number is kept finite. So in the spirit of controlling it, actually, there's a control term as well in the paper. You want to have a finite number of them and distinguish them very much from the mass of all the others. And the interaction kernels are of convolution type, basically. So you have H1, which is follower-follower interaction, K1, which is follower-leader, a possibly different K2, which is leader-follower, and H2 is leader-leader interaction, okay? This can be seen as the convolution of H with the measure, with the, say, at this level with the empirical measure. So they prove that if the particle dynamics is given by this with the uj minimizing a cost En, as I introduced before, then they can take the limit as n goes to infinity and obtain this PDE here. So they have the second order part of the Fokker-Planck equation, and then they have the divergence of this vector field, which acts in a complicated way on the measure μt. And the equation for the y's just remains in the way it was before because their number doesn't diverge. And also, as in the spirit of the mean field optimal control, there's a gamma limit result, a gamma convergence result for the cost functional in this case. And together with Stefano Almi and Francesco Solombrino, we studied a similar problem where we have a situation comparable to this one. And the last thing is that a master student of mine, Alessandro Baldi, who's now a PhD student at Politecnico di Torino, he proved the well-posedness of this equation here. So he wanted to, now this is written in the integral form, but the idea is to add stochasticity to the motion and also add the randomness in the selection of the initial data. So everything blue is stochastic in this slide, all right? Then the vector field that driving for the velocity is pretty much the same one as we had with Ambrosio, Fornaziere, and Savaret. And the F lambda field is very similar to that of the replicative dynamics. But then he can prove the well-posedness of the system and also kind of guess the mean field counterpart, which has the form of the second system here. And he manages to prove a result of a propagation of chaos, meaning that if you start with IID data at the beginning, then the dynamics happens, and in the long run, when n tends to infinity, you still obtain IID. So then what you follow basically is the law of the first player, which is X bar, and then all the others will be identically distributed with it. And he did a very nice job in obtaining these results. But this goes towards the fact that we can make more realistic models for the original problem of the replicator dynamics. And this one will go in the direction of having some sort of Fokker-Planck type equation for the as opposed to just the continuum equation. And I think my time is up. And the only thing that I want to highlight is this outlook and future directions, and then I conclude. So the idea was to study multi-agent systems with strategies or label that can evolve as well, both the positions and the probabilistic part, and to study the Lagrangian formulation, the particle formulation, and their mean field limit. Also possibly including second order effect through a Laplacian. And what we would like to do would be also try and add stochasticity in the label variable. We added the entropy, but now we would like to also add stochasticity, and this is work in progress with Alessandro Baldi and Anderson Melcher Hernandez, who was a postdoc under my supervision at Politecnico di Torino. One interesting thing for people that do more probabilistic studies is consider different types of noise. So we consider the noise with a constant term in front of it, the root of 2 sigma. Acione-Castorino-Solombrino considered additive noise. There can be multiplicative noise, or the factor in front of the Brownian motion can also depend on some other parts of the equation, making the model a little bit more complicated to study, but also more in line with other models like the CBO, the consensus-based optimization, that tells you that you reduce the noise as long as you get closer to convergence or to consensus precisely. So there's a lot of interesting problems, and with this, I really like to thank you for your attention.